everyone. So I'm Jérôme Petazzoni. I'm one of the rare people in this industry with more than 12 years of Docker experience because I was working at Docker when Docker was invented. Well, it was not necessarily a good career move because I ended up struggling with depression and burnout, but this is not the topic of today. I give talks about that in other places. So all that to say that I come here not as a data scientist, but more as a container expert, hopefully. And so my perspective is going to be informed by that. My experience with data science is very limited. I've done a little bit of computer vision, a little bit of TensorFlow, but very, very basic stuff. So I'm going to explain what I want to talk about today. I'm going to talk about Dockerfiles, how to optimize that, but also how to work without Dockerfiles. And first, a tiny little bit of stretching and yoga for everyone. Who here has already written a Dockerfile? Okay, so that's most of you. Keep your hand up if you have used multi-stage builds. So that's also a bunch of people. BuildKit cache mounts. Okay, that's almost no one except a few reruns. So okay, so there's going to be useful stuff. And by virtue of elimination, who here has never written a Dockerfile? Just a few hands as well. Okay, great. So let's get started. As a preface, when I put together this content, at first I thought, oh, I will never have enough things to say for a 30-minute talk. Turns out I actually have way too much things to say, so I decided to leave a lot of information in the slides, but I'm going to skip a lot of slides. It's normal, it's expected, but if you want to go back to the slides on your own, you can, and you can scan that QR code. It's going to give you access to the slides, and the QR code is pretty much on every slide of the presentation, so no stress if you don't have the time to scan it just right now. So what are we doing exactly? You know, why would we want to do data science in containers? I know of two main use cases. It's not the only ones, but the main ones are development environments, because, you know, I'm using a Linux machine, but maybe someone is using a Mac or a Windows machine, and we would like to have the same versions of Python and PyTorch and etc., etc. So containers are great for that, but I want to say that if you are using something else already, like Conda, and you're happy with it, then keep using it. If it's not broken, don't fix it. Another scenario is when you need to deploy on a container orchestration platform, like, for instance, Kubernetes. And a funny thing is that 7-ish years ago, when after quitting Docker, I kind of went back to working after healing my depression and burnout, and I decided to do consulting and training on Docker and Kubernetes. And very often, you know, it was the hype phase of Kubernetes, and lots of companies and teams were like, oh, please teach us Kubernetes. I'm like, okay, sure, let's look at your container images. And they were like, our container what? Like, well, if you want to run something on Kubernetes, you need a container image. There is no other way. Like, we have to start with that. You need to walk before you can run containers. So very often these Kubernetes trainings turn into Docker trainings. So that's kind of why we're here today, to talk about how we're going to put things in containers. I would like to acknowledge that we don't need to use kind of raw Kubernetes anymore. We have lots of amazing platforms that we can build on top of Kubernetes, stuff like Knative and Kubeflow, just to name a couple of these. But here, I'm going to assume that we did our research and that the conclusion was we have to put our data science things, you know, inference, training, notebooks in containers. So that's what we're going to talk about. And the use case I took here is Whisper. Whisper is a speech recognition model, and when it came out a few years ago, I was very impressed because it was able to do an excellent job, even with my French accent, even when I speak in French with a lot of technical terms. For instance, if I say, et ces features principales, ça va être les namespaces et les cgroups, it was able to correctly like parse the French and have the technical terms in the middle, and the output you see here is the raw output of Whisper, no manual editing afterwards, so that was, I was impressed. So the reason why it's interesting as an example here is because it's actual Python code with actual dependencies. You can tweak the code, you can make changes, so it looks a lot like real code that we could write and then put into containers. And also when I worked on that, I wanted to use GPUs because Whisper is like 50 times faster, give or take, with GPUs, so that was a pretty strong reason to use that. Just in case, link here if you want to see the final result of these experiments. Basically, it takes a 4-hour training video and transforms that into a YouTube playlist with subtitles and clickable and so on and so on. Nothing groundbreaking, but when you make that on your own with your own containers, it's pretty satisfying at the end. So I had many different bricks there, which is why I wanted to run that into containers. And so, of course, what I did is start with a Dockerfile. So why start with a Dockerfile? Well, first, because that's what I knew, but also Dockerfiles are pretty easy to get started with. I'm not saying that it's going to be all like rainbows and unicorns all the way, but the first Dockerfile, you know, if you know how to write a shell script, then you know how to write a Dockerfile. You just put like run in front of each line, a from in the beginning, and boom, you get a container image, and you can run Whisper in your container. Awesome. Now, when you do that, the problem here is that I was basically installing the code straight from the Git repo, which means that if I want to make changes, that's not very convenient. So then you learn about the copy command and you use that. And that works, except each time you make a single change in your code, you are rebuilding the entire container, which means downloading, in that case, about 4 gigabytes of dependencies. And I don't know how it's working for you, but optical fiber deployment in Berlin is not that great, coming from France. So it takes a while. Then the next thing we do, and I saw many hands, you know, in the beginning when I asked about Dockerfiles and everything. I'm sure that many of you already know that trick where instead of copying your entire code immediately in the container, you say, hey, copy the dependencies, install dependencies, so copy requirements.txt, install dependencies, and then copy the rest of the code. And now when I change a line of code, instead of taking 5 or 10 minutes to build, it takes just a few seconds, and that's great. That's great, but if I change a tiny dependency, you know, like I add TQDM or I change the version of anything, then I need to re-download all my dependencies, and I still don't have fiber in Berlin, so that sucks. Or if I have another project using almost the same dependencies, it needs to re-download everything, and that's not great. The solution here, and that's where hopefully this talk is suddenly going to become interesting for many of you, is to use a BuildKit cache mount. So it looks like this -- mount option, and that basically means that this particular directory, like root.cachepip, that's going to be a cache directory, so it will persist across builds of the same image, but of other images as well. So once pip has downloaded a package in there, that package will be available for other builds, and that directory, because it's a cache mount, will not be included into the final image, so we're going to also save a lot of space on the final image. So just to give you some orders of magnitude, building Whisper on my machine, on my connection, so in my non-scientific benchmark, that's like 5 minutes. And once I use this cache thing, even if I change my dependencies, it only takes 1 minute because you skip entirely the download phase. So you save time, but you also save a lot of bandwidth, and you're being like a nicer citizen of the internet for all these package mirrors and so on. Okay. Now, we started to optimize a little bit on speed, and that's great, but what about size? So my first shot at this image was 12 gigabytes. Is that big? Is that small? We're going to talk about that in a minute. Once we use the cache mount, we go to 8 gigabytes. Okay, so we saved like 1/3 of the image size, not too bad. So how does that compare to other images? I decided completely arbitrarily to have a kind of like a logarithmic system. So in my book, anything smaller than 10 megs, that's a tiny image, and that almost doesn't exist. I say almost because, of course, you're going to see very small images sometimes, but it's very rare, especially for real images with actual stuff running in it. Between 10 and 100 megs, I'm like, okay, this is pretty good. This is probably a microservice. It's probably in a compiled language like Go or Rust, or maybe it's in Python or Ruby or Node, but the people who made it put some work to optimize it. And it's still fairly rare, except for some specific images and tools. Now, the bulk of the images that we work with outside, except in data science, are going to be the next category, 100 meg to 1 gig. Most, like monolith or microservices with significant dependencies, it's going to be in that range. And then there is data science with bigger images, 1 to 10 gigs or even above, especially when we use GPUs. So this is the range where we are with Whisper. So we're going to see what we can do about it. And if we start looking at our Whisper image in the site packages directory, this is the 5 biggest packages in there. And we can see like the big culprit here is NVIDIA, 4 gigs. And so at first, my reaction was like, oh, thank you for including support for GPUs, because that's what I want to do in the end. But that's really big, and do I really want and need that? So in that particular case, I was like, can I remove GPU support? Can I have a smaller image in that case? And if you go to the PyTorch website, you're going to see like different download options. I can't really show it here because I'm using presenter mode. So if I open a link here, it won't show up there. But if you just click on that link, you will see all the download links. And there is like a pip install command that you can copy paste and tells you how to install PyTorch if you only want CPU support. So fine, we put that in our Docker file, and now we go from 8 gigs to 3 gigs, which is another pretty big improvement. By the way, I'm not showing you all the Docker files here because it would be kind of like a lot of information, but there is a repo which I call Whisper files, where you can find all the Docker files of all the experiments here, like all the different techniques, all the different optimizations. There is about like 10, 12 of them, and there is a little script to build all of them and compare the size. So so you can easily like reuse that for your own if you want. Okay, so once we've done that, we're like, okay, we're at 3 gigs. So compared to the initial 12 gigs, it's pretty good, but can we do better? We can think, oh, I could stop here. I divided the size by 4, so like reduce the size by 75%, that's a pretty good job. But if you work with containers, sometimes you see people with images of like 50 meg or 200 megs, and you're like, can I go that low? So then you see that for Python, in the Docker Hub, you have multiple kind of flavors of the base image. We have the default Python image, which is about 1 gig. Then we have the slim Python image, which is about 100 megs. And there is the Alpine image, which is half of that at 50 megs. So what's the difference? The slim image basically only has the bare minimum to run Python stuff. There is the interpreter, but it's missing a compiler. It's missing like the headers to compile Python extensions and native code. It's missing Git. So if you're trying to install packages that are on Git directly, that's not going to work. So in the case of Whisper, it actually works. We could use the slim image, and we would save 1 more gig of the size of the image. Like for GPU, you go from 8 to 7. For CPU, from 3.4 to 2.3. So that's pretty good. Now, what about Alpine? Alpine is even smaller, and one of the reasons why it's even smaller, not the only reason, but one of the pretty big differences in Alpine is that it's using MUSL. MUSL is an alternative system library, so it kind of comes instead of the GNU C library or the glibc. So on the one hand, it's great because you can have like really small binaries, really small images, and if you do container image optimization, at some point you're bound to run into Alpine. The downside is that most libraries and binaries compiled for Alpine will not work on a glibc system. To say that differently, if you take a package for Alpine, it won't work on Debian, Ubuntu, Fedora, CentOS, and so on, and vice versa. Of course, caveats, there are some exceptions, there are some compatibility layers that mostly don't work outside of trivial scenarios. So here, can we actually use Alpine for data science? And well, mostly no, in the sense that the biggest packages like TensorFlow and PyTorch don't work on Alpine. I mean, not officially. Some folks manage to get them to work with some hacks, but it's not something I would recommend. So sure, some other packages though are getting there. A couple of years ago when I was working on all that, if you wanted to get even like NumPy or SciPy for instance, it was kind of dicey on Alpine, and now it works just fine. So there's definitely progress happening, but the really big ones that we want to use in that case are not available yet on Alpine, so unfortunately we can't use Alpine for this, but it's definitely something to keep on the radar. Now, earlier I asked about multi-stage builds, and I saw that many people knew about multi-stage builds. So multi-stage builds are typically used when you are building images for compiled languages. C, Go, Rust, these are like the perfect examples for multi-stage builds, and usually for Python, Ruby, and other interpreted languages, we're like, why would I use a multi-stage build? Because the whole point of the multi-stage build is to have one stage, so one image, if you will, where you build, you compile, and then you take the binary and you put it in a run stage. So it's a way, like functionally, it's a way to remove the compiler from the final image. So here, at first, we could think, well, we don't need that for Python, because in Python, we don't compile stuff. We don't, except when we do, so except when we install packages that have native code. Here, it's a little bit of a gray area, because most popular packages these days will be available as compiled wheels as well. So for instance, when you install NumPy or SciPy, there is a lot of native code in there. And so I would say maybe 5 years ago, when you installed them, it would need to compile a bunch of things, especially if you installed them on ARM or on Alpine. But nowadays, we have these pre-compiled wheels. So when you install them, Python, well, pip is going to check, do we have a binary wheel for your particular architecture and your particular version of Python and the particular system library that you're using? If so, it's going to use it. Otherwise, it's going to try and compile that native code. And in that particular scenario, if you are using a package that doesn't have a precompiled native version, then multi-stage builds can help. A quick and dirty way to leverage that is to copy the site packages directory from a build stage to a run stage. I say quick and dirty because it feels kind of gross to do that kind of thing. You're just like copying a bunch of libraries and YOLO, hoping that it's gonna work. A better way to do this is to leverage virtual envs. And that's kind of weird at first, because we might think, wait a minute, virtual envs, it's what we use when we want to separate environments. If I'm using containers, why would I use a virtual env? Well, precisely to have a single directory where we're going to have the Python interpreters and all the packages, everything, and we'll be able to just copy that in the final run stage. So again, that's very specific. It's when I have extensions and these, packages that use native code and that code is not precompiled. Something else that we can do, and here we have a perfect example with Whisper. Whisper is using FFmpeg to transcode and convert audio formats. And very often when you install a package coming from a repository, that package is going to be in what I call Christmas tree mode. So as a package maintainer, I enable all the options and all the dependencies so that my package is the most useful for everyone. So what we can do here is compile our own smaller FFmpeg. In that particular case, I found a static version of FFmpeg that had a reduced set of codecs, and that saved me 500 megs on the image. Now, would I use that in a proper, enterprise data science pipeline? Not quite. I would not take some random person's binary to put that in my containers. What I would do in that case is probably reach out to that person and ask if they're willing to share the scripts that they use to build FFmpeg, and then I would put that in my own pipeline. All right. So if we kind of summarize, we went from 12 and something gigs at first, and once you leverage everything I mentioned here, we go down to 1.8 gigs. So we divided by, what, 6, 8, the size of the image. That's not too bad. However, if we want GPU support, this kind of goes back up to 6 gigs. So it's still nothing to laugh at, but it's still a pretty big image, and because of the NVIDIA drivers, it's really hard to go lower than that. Okay, so what else I want to say? Right, when building variations of images, so for instance, in that case, a CPU or GPU, maybe I want to change to a different version of PyTorch, a different version of CUDA, a different version of Python, and so on and so on. One thing we can do is use build arguments. And so that way, instead of having an impossible matrix of 5 times 3 times 7 Docker files, you can have a single Docker file and use these variables that you set at build times. It's just like environment variables, but only used during build times. Now, what about models? Because if we look at Whisper, we have gigs and gigs of models. And so the question is, should we, the good news is that each time you need one of these models, Whisper is going to download it automatically, I believe from Hugging Face. The bad news is that it's going to download it each time you restart the container, because each time you restart the container, you start with a blank slate, the models are gone, and they need to be downloaded again. So, should we put the models in the image? I happen to have really strong opinions about this, and it's no, please do not. And to explain, okay, first exceptions, if the models are really, really small, or if they never change, okay, then maybe put them in the image, no big deal. But otherwise, the problem is that we just spent, I don't know, like 20 minutes talking about how to get the image to be smaller, and now we're like, hey, now let's add like 4 gigs of model weights and parameters in there. So registries are not always a really efficient way to distribute big assets like this. It can often be better to use an object store. I said not always because there is a trend to actually store static assets in container registries, not really for the performance, but for authentication purposes, because that way you just have to deal with how do I authenticate to my registry, and then you pull everything from the registry. Instead, I recommend to use volumes, and just to give you a tiny example of what that looks like, if you're using like local development containers with Compose, this means this directory is mounted into the container, so the first time it's going to pull the model, and on subsequent runs it's going to use these models. And we have the same thing on Kubernetes. Okay, so I spent most of the talk on Dockerfiles, but what about not Dockerfiles? What if I don't like Dockerfiles? Do we have other solutions? We have language-specific tools. So if you're doing Java, there is Jib. If you're doing Go, there is Go. I'm not aware of Python-specific tools to build container images, but if you do know some, let me know. We also have things like build packs. The pitch of build packs is, wow, these Docker files are so complicated, like it's giving me a headache. I just want to throw my code at it, and I want to get a container image. And that's what build packs do, and they do it quite well, except when you do it on something like Whisper, you get an almost 30 gigabytes image, and in spite of my efforts, I was not able to get that to a significantly lower number, and also the build is really, really slow, and again, I could not find ways to make it faster on something like Whisper. So build packs can be awesome in some scenarios, like recently I was doing some Java Spring AI stuff, and I was like, wow, their image is as small as the one I made with all my container experience, so great, but for data science, unfortunately, that was not that great. Same department, we have OpenShift source to image. I wasn't able to get it to work, and the documentation is still mentioning some really old versions of CentOS and Python, so I don't know if that actually works and still is maintained. Happy to have a conversation about it after. And we have some tools like Bazel or Nix, and the short spiel here is that if you already know Bazel or Nix, then absolutely use them, all the power to you, but I do not suggest that you learn them solely to build container images because it's a huge learning curve. You know, it's like, oh, I'm going to learn TensorFlow because I need to do my accounting. I'm not sure. So one last thing I want to mention is lazy pooling. When you have really big images and you do some Kubernetes auto-scaling and you're like, I'm waiting for 5 minutes for my image to pool, and meanwhile I have like a traffic spike. Lazy pooling means the ability to start a container before the image is fully downloaded. It works great for images that have a ton of packages and dependencies. It works not so great, for instance, for Jupyter notebooks, because for the notebook to start, you need to access a lot of files anyway, and in that case, the savings of the lazy pooling method are going to be not that great. So to wrap up, as you probably could guess, like my suggestion here is, well, let's use Dockerfiles because it's really easy to get started, and then little by little we can add more optimizations and more improvements as we go. There are many things that we can do. I listed a few techniques here. Without Dockerfiles, as I tried to show, there are some solutions that exist, but it's pretty hard for me to recommend them because even with my experience with containers, I was not able to get something satisfactory for my particular use case. It doesn't mean they're bad, it just means that at least for these scenarios, maybe they're not the best options. So I'm going to wrap up with a bunch of links. So I mentioned Whisper files, this repo with about a dozen of Docker files, specifically for Whisper, but you can get inspiration there for pretty much any Python app, data science or not. I also have another repo called min images, which at some point I could probably rename as like 50 shades of Docker files. It has like more than 50 Docker files, not just for Python, but also like Go, Rust, Java, showing many different techniques and optimizations. So for Java, we even do like native builds and so on. And so to illustrate like multi-stage and caching layers and so on and so on. And finally, I think I was mentioning that briefly in the beginning, but now my main job is to do consulting and training on Docker and Kubernetes. So if your team needs help on these topics, feel free to reach out. I've put my LinkedIn here. I think there is also my Mastodon information in the beginning of the talk. And now we have, I think, a couple of minutes left for questions.
Okay, we have one question here.
Hi, thanks, great talk. Did you try using UV instead of pip when you were doing the installations, which I suspect might make the installation time quicker?
Did I try to use UV? No, I haven't in containers, but I think you're right. It could make a few things a little bit faster. I hope that it would be really easy to test with the Docker files I have. So I think I'm going to try that this afternoon and see what happens. Yeah.
Hello. Is there any technique specific to CI/CD pipelines, like the caching part, when the pipeline doesn't have any cache from before?
Technique specific to what pipelines you said?
CI/CD pipelines, like GitLab pipelines or GitHub pipelines and
Right,
stuff.
yeah, absolutely. So this, for CI/CD, I had a few slides on that, but I skipped them. But absolutely, the trick with the cache is that very often, if we build with platforms like, let's say, GitHub Actions, each time you start a new build, it's a completely like brand new environment, and the cache is gone. So I kind of explained that in the slides, but the idea is that the Docker builders have this caching backends mechanism where you can say at the beginning of the build, pull the cache from there, and at the end, push it back there. And the backends could be an S3 compatible object store. It could be a local directory. They also have stuff specific to GitHub Actions, and that works pretty well. Of course, it means a little extra delay because you need to pull and push that cache, and that cache can be pretty big, but it's still faster than pulling the packages because it's just, basically it's just like downloading a bunch of bytes instead of downloading from a mirror and installing and resolving dependencies and so on and so on. And very often, of course, you will set up that cache backend so that it's really close to the builders. So, yeah.
Any other questions? Then, thank you, Jérôme. Some applause to Jérôme.